Good evening. In the last session, we discussed about fluids at rest in our chapter, Mechanical Properties of Fluids. And today we move on to hydrodynamics, which is a study of fluids in motion. And we start this hydrodynamics with our equation of continuity. Okay. So what I've drawn here is a pipe of non-uniform area of cross-section, because you see here the area of cross-section is larger, A1, and at the other end we have a smaller area of cross-section, A2. So this is a pipe of non-uniform area of cross-section, and in this pipe we have a fluid which is in steady flow and it is an incompressible fluid. Incompressible fluid means the density is a constant. So throughout we take the density to be a constant, and that is what you mean by incompressible fluid, and the fluid is in steady flow. Now, as the fluid enters through one end and flows out through the other end, in time delta t, the volume of liquid entering through one end must be equal to the volume of fluid flowing out at the other end in the same time interval delta t. So if the volume is a constant, let's say the volume entering and the volume leaving, both in time delta t is delta v, it means that the mass also must be the same, because mass we know is volume into density, because density is a constant and in time delta t the same volume is entering and leaving. We know that the mass of liquid or fluid entering at end A must be the mass of fluid coming out at the other end B. For example, if 1 kilogram of fluid enters, then 1 kilogram of fluid must come out of the pipe in that time interval delta t. So naturally, we know, now if you take delta t to be a very small interval of time, then we know that this distance, in this distance we may consider this to be the same, the area to be the same, so that the volume of this cylindrical portion will be base area into height. So here also the volume will be base area into height. Now this distance it flows, distance we know is equal to velocity into time, because velocity is distance by time. So at this end, the distance traveled in time delta t by the fluid will be v1 into delta t, and at the other end the speed has to be different, because if the volume has to be the same, when the area of cross section is larger, then the height should be smaller, because we know volume is equal to base area into height. Base area into height. So when the base area is large, the height, the distance traveled will be smaller. When the area of cross section becomes smaller, the distance traveled becomes larger. So this is what we have here. So we know that the mass of fluid entering at end A must be equal to the mass of fluid coming out at end here 2 in the same time interval delta t. Mass we know is volume into density. So we may write volume is base area into height. So this area here is A1. The distance traveled, which is the height of that cylindrical column of fluid, is V1 delta t, using this distance equal to velocity into time. This should be equal to, at the other end, the base area is A2. The height is V2 delta t. So if I cancel this here, we see that A1 V1 is equal to A2 V2, or we may write AV is a constant, which is equation of continuity. So that means larger the area of cross section, smaller the velocity, smaller the area of cross section, larger will be the fluid velocity. This is best explained from our example, where suppose you are watering plants in your garden. If you want the water to flow further away from you at a larger velocity, you use your finger to close that hole of that hose pipe, so that the area of cross section of that hole becomes smaller. Smaller the hole, greater will be the velocity. If you want the water to flow close to you, fall close to you, then you remove your finger so that the hole becomes larger. Greater the area of cross section, smaller will be the velocity. So this is equation of continuity. And from here we move on to Bernoulli's equation. So the next topic that we will be studying is Bernoulli's equation. Here also we consider a pipe of non-uniform area of cross section. So we have a pipe here of non-uniform area of cross section. And here this is at a height h1, this is at a height h2, and we have pressure P1 at end 1, pressure here is P2 at end 2. Of course, the area of cross section here is A1, area of cross section here is A2. Like before, the fluid is in a non-uniform pipe. Area of cross section is non-uniform. It is in steady flow and it is incompressible, meaning the density remains a constant. Also, the two ends of the pipe are at two different heights. This is at a height h2 and this is at a height h1. Okay, so here in time delta t, like I told you before, the fluid flows through a distance v1 delta t, because we know the distance traveled is velocity into time. And when you reach here, the smaller the area of cross section, larger will be the velocity. So we have the distance covered at this end will be v2 delta t. Now here what we are going to apply is the work energy theorem, which you did in chapter work energy power, which says the work done is equal to the change in energy. Here there is a change in kinetic energy, because you see smaller the area of cross section, larger will be the velocity. So there is a change in kinetic energy. There is also a change in potential energy, because this end is at a height h2, which is larger than the height h1. So there is change in kinetic energy and change in potential energy. So the total change in energy will be equated to the work done. Now here at this end, the work is done on the fluid to push it into the pipe. So work is done on the fluid, which is taken as positive. At the other end, the fluid is coming out. So work is done by the fluid, which is taken as negative. So let's find out work done. I will call work done at the first end here as W1, which is going to be positive, because I told you work is done on the fluid to push it into the pipe. Work done we know is force into displacement. Force we know is pressure into area, because pressure is force by area. And the pressure at this end is P1, area is A1, into displacement we know is V1 delta T. So we have V1 delta T. Here A1 V1 delta T should be the volume of fluid entering the pipe, because V1 delta T is the height and A1 is the base area. Base area into height we know is the volume. So we may write this as P1 into delta V, because you know that in time delta T, the volume entering at end A must be equal to the volume of fluid flowing out at end here at 2. So delta V will remain the same whether it is end A or the other end here 1 or 2, because you know in time delta T same volume will no change in volume. So W2, which is the work done by the fluid in coming out of the tube, is taken as negative. So this is going to be minus force into displacement, which is pressure into area into the displacement here is V2 delta T. Here again we know that A1 V1 equal to A2 V2, right? So A1 V1 delta T and A2 V2 delta T are the same volume. So this is minus P2 delta V. So we may write the net work done should be equal to W1. We'll add the 2. So this may be written as P1 minus P2 bracket delta V, which is my first equation, where delta V is the volume of fluid entering the pipe in time delta T equal to the volume of fluid flowing out of the pipe in time delta T. Now this net work done has to be equated to the change in kinetic energy and the change in potential energy. So change in kinetic energy we know is half mv square. So we have half m. At this end it is V2 and this end it is V1. So this is going to be V2 square minus V1 square, where V2 is larger than V1, because you see a smaller area of cross section, we know V2 will be larger. Now mass I told you is volume into density. So I may replace this as half, volume is delta V, density is rho, V2 square minus V1 square, which is equation 2. Then we need to write the change in potential energy. Potential energy is higher here because H2 is larger than H1. So we have change in potential energy delta U as mgh, which is mass. Again I will replace with volume into density. So delta V rho gh, which is equation 3. And by work energy theorem, we know we can equate the work done to change in energy. So equation 1, which says P1 minus P2 delta V must be equal to change in kinetic energy is half delta V rho V2 square minus V1 square plus delta V rho GH. So we now have I'm going to cancel delta V, which is common everywhere, here and here. So we have P1 minus P2 equal to half rho V2 square minus V1 square, and the last term is plus rho G. Oh, there's a mistake here. This is H2 minus H1. Because you just saw that here it was higher. So here the this is change in potential energy is mg H2 minus H1, because this here it was H2 and at this end it was H1, right? So here it is mg H2, here the potential energy is mg H1. The change will be mg H2 minus mg H1. So mg H2 minus mg H1, which gives me this as H2 minus H1, which is equation 3. So we have here so we have here H2 minus H1. So that this will be rho G H2 minus H1. Now I'm going to bring all the 1 terms to the left and 2 terms to the right. So this will be P1 rho half rho V1 square. When I bring it to the left, it becomes plus half rho V1 square. When I bring rho G H1 to the left, it becomes plus rho G H1 equal to, I bring P2 to the right, P2 plus half rho V2 square plus rho G H2, which means P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2, which means I may write P plus half rho V square plus rho G H must remain always a constant. And this is Bernoulli's equation. Now in a statement, so if you notice, this half rho V square should be the kinetic energy per unit volume. Let me show you how. Now kinetic energy we know is half mv square. This I may write as masses volume into density. So delta V into rho into V square. Now this is kinetic energy. When I say per unit volume, I divide by delta V. So if this gets cancelled, you know now that this actually is kinetic energy per unit volume. Similarly, let us look at rho GH. Now potential energy we know is mgh, mass is volume into density into h. So this is also potential energy total. If for unit volume, if I divide by delta V, I get this rho GH. So this rho GH is actually potential energy per unit volume. So this is potential energy per unit volume, which means as a statement I may state Bernoulli's equation as the sum of, for a fluid which is in steady flow, for an incompressible fluid in steady flow, the sum of the pressure plus the kinetic energy per unit volume plus the potential energy per unit volume remains a constant. So this is Bernoulli's equation. So in our class today, in hydrodynamics, we discussed equation of continuity and Bernoulli's equation. Thank you.